At 12 p.m., noon, a train departs from Central City, traveling due north at 20 miles per hour. At 1 p.m., a second train departs from Central City, traveling due east at 30 miles per hour. At what speed are the trains moving away from each other at 2 p.m.? And all the answers are in miles per hour, so that's good. We've got 34, 38, 42, 46, and 50. We have an answer. Well, the answer is not 42, even though there's a saying, 42 is the answer to life, the universe, and everything. The answer is A. So what's happening? Well, we have our central city, and we have the trains are moving, and they're moving at right angles to each other, so that makes things a lot easier. Now, the reason we had them depart at different times was so that they could be at a very convenient distances, but also be at relatively different speeds. So, because your train traveling north has going at 20 miles per hour, but it's had 2 hours, it's gone 40 miles, going 20 miles per hour. The train traveling east has only been going for 1 hour, so it's gone 30 miles, and it's going 30 miles per hour. This distance, well, 30, 40, 50. 3, 4, 5 right triangle. What do we need to find? Well, how far the trains are moving from each other, dz dt. So we take the derivative with respect to time, cancel off our 2's, plug in what you know, and solve. 34. There we go. What a fun problem. Related rates. They love related rates problems. Any questions? All right. Well, on to our thought for the day. So today's thought for the day. It's dangerous to go alone. This is from Legend of Zelda. And even though I am quite old, I will admit that I really only got into Zelda with Breath of the Wild. And but okay, why is this my thought for the day? Well, I think sometimes math gets this impression of being like if you've seen the movie A Beautiful Mind, where you have this really eccentric person working alone, writing on windows, you know. And so somehow math is this solitary thing meant for strange, weird, but somehow at the same time smart people. But I don't think that captures what math is. Math is a very human activity, and it should be done by humans with other humans. And it's a lot more fun and a lot faster to learn when you learn with others. So you should not go alone into math. And as you are comfortable and able, I encourage you to work with others. Talk to each other. Bounce ideas off of each other. Explain things to each other. And if you have no one else available, you still have your duck. And it's an important thing, working together. And we're at that time in the course where people start thinking, should I stay in the course or should I change? And before you go, I do want to say, I hope you stay, by the way. I'm not asking people to go. But if it's the right thing for you to go, I'm happy for you. I want you to do what's best for you. But before you go, I want to say that math is a human activity. And as such, it's sometimes gets sort of human things get involved. And you can have mathematical trauma. A bad math experience with a teacher can affect your view of math and how you think about yourself in math. But it's not just that. Your parents could have had a bad math teacher 25, 30 years ago, and it affected their views of math. And you inherited their mathematical trauma. And what I want you to know is that we want you to start to feel better about math, and you and math should, we hope you get along. Start healing that trauma if there is any. So, and hopefully, when you pass on to the next generation, you're going to pass on positive vibes, like, oh, I love math. It was great. All right. So, last time, I feel like we didn't give you enough opportunities to work. So I thought, let's finish up, do one more related rates problem. So this came from a calculus final. And it was one of the most meta problems I've ever written. While thinking about a question on your calculus final, you begin rolling up your 8.5 by 11 inch exam long ways, forming an 11-inch tall cylinder. You then let the exam uncurl so that the radius of the cylinder increases at a rate of 1/3 inches per second. At what rate is the volume enclosed by the exam changing when the circumference is 6 inches? So, do we have an answer? Is someone like, I see it, the answer is, whoa. I see someone cautiously raising their hand. Yes. 22. Is it 22? It is 22. All right, so what's going on? Now, we know it's related rates because we see a couple of rates involved. When we see multiple rates, it's related rates. There's this rate of the radius. We want rate of volume. So we know there's a dr dt and dv dt. So we say, okay, we want to connect radius and volume. Now the thing is, volume is pi r squared h, but the paper's height isn't changing. It's always 11 inches. So we can plug in h equals 11. So volume is 11 pi r squared. We know dr dt, and because we know the circumference, we know r. Take the derivative, plug stuff in, and we get 22. And this is because I had a typo. So yes. And unfortunately, markers don't erase. So 22, yeah. See, you guys can do final level problems. So, any questions?
The bug is back.
Is it? Wow. I don't want to hurt it. It's okay, little bug. Be you. I think it's attracted to the light. Don't go to the light. Okay, so today's topic. So we're talking about linearization. Now the goal is you have this function f of x. So we have f of x. Here's f of x. And you have a point A. And you say, okay, so here is A. Now the goal is to say, I want to find a line. So that's, you'll notice how linearization starts with the word line. I want to find a line, which is, and somehow it's the best line. It's the line which most captures what f of x is doing near x equals a. And so we say, well, gosh, can we think of a line that really mimics the behavior of the function at that point? Yeah. So if we are a nice function, in other words, all the functions that we see, then the best line, the linearization, is the tangent line. So we basically have already talked about linearization. Now we're just giving it another name. So tangent lines are linearizations. And another way to say this is tangent lines are approximations to the function. So they're approximations to the function near the point of tangency. And there's this note here that the approximation is good near A. But the further away you move, the worse the approximation gets. So if you're using linearization, you're using approximations, you have to keep that in mind. You're saying, I have to be close to something useful. Another way, or possibly an argument, if you will, why is the tangent line the best line? Well, if you think about the definition of the derivative, which hopefully you're like, nope, I'm not thinking about that anymore. But it's that limit as h goes to 0, f of x minus f of a over x minus a. Well, you can say, well, this is approximately f of x minus f of a over x minus a. Oh, sorry, not h goes to 0. This is x goes to a, excuse me. And if you just start and rearrange this, multiply by x minus a and move the f of a across, what you get is that f of x is approximately f of a plus f prime of a times x minus a. So in other words, this linearization follows from the definition of the derivative. So, okay, it's a very reasonable thing to say. Tangent lines are the bestest lines. All right, so let's use this. So we're going to do lots of approximations. So you're going to see some words. So if you see words approximate, estimate, those are saying you're not after an exact answer. You're after a reasonably close answer. And that's when we pull out these tools. So these are all about getting sort of guesses, good guesses, if you will. So let's do a problem. Use a linearization of f of x, which is the square root of x, to get an approximation of square root of 65. Now, there's a word here, a linearization. Well, why would they say a linearization? How many linearizations of square root of x are there? Sorry, what? There are infinitely many linearizations because every single tangent line to my curve gives me a linearization. So there's tons of linearizations of square root of x. So it's like, oh, so now that there's lots of linearizations of square root of x, you have to start thinking about what's the one to use. So the answer is you have to use ones that you can actually hope to get progress in. And you say, okay, well, let's think about square root of x. And we really say, look, if I'm thinking about square root of 65, well, square root of 65, that's f of 65. So now we're starting to say, let's think of the number 65. Are there numbers close to 65 which are really nice for the function, which we understand well? 64. 65 is close to 64. And 64 is nice. So the great aha is for us to say, oh, we should use the linearization at 64. So we're going to do linearization at 64. Because it has that perfect blend of being close to 65, but being nice to work with for the function. All right, well, so let's get some information here. We have f of x. Square root of x, we say, let's write that in calculus-friendly language. What is f prime of x? 1/2 x to the negative 1/2, if you like. If you want to go back to the uncalculus-friendly way, that's 1/2 square root of x. All right. And let's think about this. Now, what's going to happen is we're going to plug in. So we're plugging in 64. So f of 64, square root of 64, also known as 8. All right. F prime of 64, that's 1/2 square root of 64, which is over 16. Okay, so now we had the function, we had the derivative, we plugged in. That gives us information, and we say, okay, this gives us a tangent line. So we say, okay, the tangent line, which is the linear approximation, so f of x is approximately the function at 64, 8, plus the derivative at 64, 1/16, x minus 64. So this is f of 64 This is f prime of 64. All right, and we're basically done. Now, I said f of x, but this is square root of x. And this is near x equals 64. So, near x 64, we've come to the conclusion that square root of x is approximately 8 plus 1/16 times x minus 64. Are we done? What's left for us to do? Plug in 65, right? Because we want 65. So, square root of 65, that's f of 65, is going to be about 8 plus 1 over 16 times 65 minus 64. Well, 65 minus 64 is 1, so this is 8 plus 1 over 16. And let's see, 1 over 16 is a number. Let's see, is there anything else we can say about that? It's 8 point... Well, it couldn't have been 1 over 8, because 1 over 8 is 0.125. So this is 0.06625 maybe? Or does anyone know?
What was it? What was 0.8? 0.8 was...
Well,
0.8 was like what?
0.0625.
0.0625? 0.0625. Okay, cool. Now, that's the approximation. Of course, we'll never know exactly what square root of 65 is, because, you know, is there any technology that could answer that for us? Now, actually, there is technology. Does anybody have their phone handy and say, well, because I always hear this, why do I need calculus? I always have my phone. But now we'll find out. How does calculus do versus a phone?
That's pretty good.
So square root of 65 is actually?
8.062257.
Not bad. We match. At least the first 3 digits. So, not a bad estimate, given that when you think about it, we weren't really doing very much. You might say, can you do better? Yes. When will we learn that? Next semester. It's going to be the part of Calc 2 that causes the most trauma. But because we'll do it together, we're going to do it as a group. We're going to have a healing experience when we go through it. So that's something to look forward to next semester. All right. Any questions on this one? So, similar problem. Use linearization to estimate the cubed root of 137. And we'll just make an observation here that 5 cubed is 125. 5.16. That's pretty right. So, 5.16. Now, the nice thing is, it really is 5.16 is the estimate. It's not like I'm rounding. And I will say, if you are checking with your calculator and you take the cubed root of 137, I don't remember what it is, but I do know that if you rounded it to 2 digits, 2 decimals, you get 5.16. So it's not a bad estimate. So what's the insight? Well, you have to think about what haven't they told us in this problem. They didn't tell us the function to use. So we had to figure that out. So what's the right function? Well, it's the cubed root function. What tells us it should be the cubed root function?
The 3 square root of whatever.
Well, what tells us it should be a cubed root function is because we're doing the cubed root of something, right? You're thinking of a function as you plug something into something. And it's like, I put 137 into this machine called the cubed root. So the first thing is to recognize there's a function I should use. the other thing is to say, well, what number should I pick? And they kind of told us what to pick. It's 125. If you went with 4 cubed, that's 64. Well, that seems too low. 6 cubed, what is 6 cubed? 200 and something. It's too big. Why don't I know 6 cubed off the top of my head? I feel old now. It's 216. 7 cubed, of course, we all know is 343 because it's just such a great number. It just rolls off the tongue. But okay, so 5, that's the sweet spot. It's relatively close. So now that we know the plan, we're finding the tangent line to x to the 1/3 at the point 125. Find our function derivative, plug in. We have our tangent line. Don't expand. Leave it in this form. Plug in the point you want, 137. Well, 137 subtract 125 is 12. Then 12 over 75 becomes 4 over 25, which you can make 16 over 100, which is 0.16. Good times, good times. This was back in the day when I was in my 137 phase. So for a while, I tried to put 137 into all my problems. But then Rick and Morty came along and started copying me. Like, they put 137 in. Like, God, I can't do that. It's a nice number. Yeah. It also turns out the universe has this very strange constant, 137, that seems to dictate everything. We don't know why. But, all right. So, there is another viewpoint on linearization. So if you move the f of a term to the other side, then what you get is you get f of x minus f of a. That's approximately f prime of a times x minus a. And you say, well, the f of x minus f of a, that's your change in your output, change in y. And x minus a, that's your change in your input, change in x. So I could say, oh, if I want to understand my change in my output, I can estimate that, because that's these squiggly lines is about. It's estimation. It's about the derivative times the change in the input. So we can use information about changes in output to get information about changes in input, and vice versa. So here's an example of how we could use it. So suppose you have this function, y equals 5x cubed minus 4e to the power 3x minus 6. And we're told that x is 2 plus or minus 0.05. So we know x approximately. We want it to be 2, but there might be a little bit of noise. It turns out life is fuzzy. You know, you never get exactly 2. You get like 2.04 or something. You get something close to 2. And so you say, okay, suppose we have a sort of a range for x. What's the range for y? Now you could say, well, if everything were perfect, so I could say I have this function f of x is this 5x cubed minus 4e to 3x minus 6. If I just plugged in 2, well, that would be 5 times 2 cubed minus 4 e to the power 6 minus 6. 6 minus 6 is 0. E to the 0, 1. 2 cubed, 8. So 40 minus 4, 36. So that's if things were exact. But we have this sort of fuzz. All right, so we have to say, how much might we be perturbed by in the output? Given that our x might change, so will our y. So now we can say, well, to figure out this right here, this is our delta x. And so we say, hey, we've got our delta x. We want to understand our delta y. This is what will connect them. So we take our derivative, f prime of x. Well, what's the root of 5x cubed? 15x squared. What's the root of 4e to the power 3x minus 6?
3x minus 6 e to the 3x minus 6.
Wait, what?
Down here.
So what's the constant in front?
It's just going to be 12 e to the 3x.
12e to the 3x minus 6, right? So it'll be 4, e to something, the derivative of e to something is e to that something, take the derivative of the upstairs, that adds a 3 downstairs. So that's 4 times 3 is 12. Okay, so f prime of 2. Well, 15 times 2 squared minus 12. 15 times 4, 60. 60 subtract 12, 48. So we get that our delta y is approximately f prime of 2, which is 48, delta x. Well, here's our delta x. So that's 48 times 0.05. And if you take 48 times 0.05, you get a number, 2.4. All right. If you're wondering how you come up with that, there's calculators when you're not in a test or a quiz. If you are in a test or a quiz, think of it as, what if I doubled 0.05? What would that be? 0.1. And 48 times 0.1 is 4.8. Now undouble, which means divide by 2 to get 2.4. So there's ways to think about things. So what's our answer for what's the corresponding range for y? Well, ideally the range, it should be 36, but we might be off by up to 2.4. So this is the range for y. And pictorially what's going on here is we can think of it as we have a function. So we have our y equals f of x. Okay, so here's f of x. And here we have our 2. And we want to go within this range here. So the question is, what's the corresponding range for our output? How do we figure that out? Well, the way we figure it out is we say, well, let's pretend as though the function were just the tangent line. So what we're doing is we're treating the function by the tangent line and say, hey, the tangent line, that's easy to figure it out because flat things are easy to figure out. And so we'll use the information about the flat thing to figure out a good reasonable estimate for the non-flat thing. All right. I think we have enough time to read the next problem. This is a fun one. And if you have a hard time reading it on the screen, now imagine you had to take this on a test because this came from an old exam. And it's also on the handout. So if you don't want to read it from the screen, you can read it from the handout. I'll read it out loud and I'll pause as needed. So, you have recently been hired as the chief architect for a pyramid being constructed by Pharaoh Sneferu in Egypt. That's going to look pretty good on your resume. After consultation, the Pharaoh has agreed to a pyramid design, 500 cubits wide at the base and 300 cubits high. So, okay, so pyramids look like you have 4 sides on the bottom and then you go up. So, we're told we want 500 on the base and the height is 300. And cubits is a measurement that was used in ancient Egypt. So the volume of a pyramid is 1/3 b squared h. That sounds important. I'll write that down. That sounds like a math thing. So as I see math things, I saw like, 500 heights, 500 width, 1/3 b squared h. As I see math things, I said, let me pay attention. So b is the length of one side of the base, and h is the height. So the pyramid needs 25 million cubic cubits. Now, you might be wondering, did you write this problem just so you could put in the cubic cubits? It was a motivation. I won't lie to you. All right, so we need 25 million cubic cubits of stone. When you get in touch with your stone contractor, because of course that's how they did it in ancient Egypt, you discovered that there are only 23 million cubic cubits of stone available. Uh-oh. But, good news. The pharaoh approves making a smaller pyramid. But it has to have the same proportions as before. So you can't just like shrink in one of the two dimensions. You have to shrink it so it looks like the same thing, but just slightly smaller. So, use linearization to estimate how many cubits smaller the base of the pyramid will be. So what is our goal here? Well, we're trying to figure out change in the base, delta B. What do we have? Well, we have change in the volume because we've changed how much is available. How much has our volume gone down by? 2 million. And it's gone down, so it's a negative. So negative 2 million. So we want to find delta B. We don't want to find delta B. We're given. Okay, so is there something that connects B and V together? Yeah, we have this formula. Now, what's the problem with this formula? You have H. So here's the thing. How do we get rid of the H? Well, here's the great aha. B and H will scale together. So we can say the following. B is to H. In whatever pyramid we pick, we scale these dimensions as 500 is to 300. That's the scale in the original design. So, what does that say about H? If you solve for H, 3/5 B. So, volume is 1/3 B squared times 3/5 B. 3's cancel. You get 1/5 B cubed. So, linearization says delta V, it'll be approximately something times delta B. We need to figure this term out. So what are we going to do? Well, what goes here, this is our, what we would call V prime of base is 500. So we're thinking of V as a function of B. So we're going to take the derivative at 500 because that's where our initial base was. What is V prime? V prime of B.
Isn't it 2/3? 3/5 B.
3/5 B squared. So, plug in 500. V prime of 500 is 3/5 times 500 squared, which is 1,5 with 4 zeros, 150,000. Where did the 4 zeros come from? Because you had 2 zeros here. That's like 100. 100 squared is 10,000. 5 squared is 25, but divided by 5 is 5 times 3 is 15. So 150,000. So this is 150,000. Now, let's plug in. We're almost done, right? Delta V minus 2 million is about 150,000 delta B. So let's cancel a whole bunch of zeros. We can cancel 1, 2, 3, 4 zeros on both sides. Minus 200 is about 15 delta B. So delta B is about minus 200. It's not surprising that it's negative because it's going to be smaller. Can we cancel anything else? We can pull out a 5 and cancel. So we get negative 40/3. All right, so we shrink the base by 40/3 cubits. So that's the shrinking. Now, you might have questions. Was Sneferu a real pharaoh? Yes. Did he build a pyramid? Yes. What is that pyramid famous for? It's famous for looking like this. It started going up, and then it's like, nope, that's not going to work, and they changed the angle. That's why you never shortchange your stone contractor. So, all right. I guess we'll stop there for today. Have a good day.